Conditional probability is giving us a probability based on knowing something else has already happened. So in the last section, we learned that when two events are independent, the occurrence of one event has no effect on the probability of the second event, but we can't always assume that two events will be independent. So then we can end up with this conditional probability. This notation, which is the probability of event F given E, so everybody read that, the probability, repeat after me, the probability of F given E. Great, that's what we're reading when we read this, is the probability that the event F occurs given that we know event E has already occurred. If E and F are any two events, then this is the formula that we're going to use for conditional probability in both the format with the word and with the intersection symbol. The only reason that there's two options is that you can do conditional probability if you were given probabilities or if you are given the number of times something has occurred, which we know we can do probabilities from anyways. So let's see what this looks like in general. Suppose a single die is rolled. The first question for us is going to be the probability that the die comes up 3. To do a probability, we need to know the sample space. What is the sample space of a regularly rolled die? 1 through 6, right? Yeah. So the sample space for this is 1, 2, 3, 4, 5, and 6. So the probability that we would get a 3 ends up being the probability or the number of times you have the number 3 in your sample space over the total number of numbers in your sample space. So how many times does the number 3 occur in my sample space? 1 time out of how many numbers in my sample space? 6. So we have a 1/6 chance of rolling a 3 when we roll a die. That's not conditional probability. That's classical probability. But let's now suppose that the die is rolled a second time, but we are told that the outcome will be an odd number. What is now the probability that the die comes up 3? What happens here is that our sample space changes. We know that it's going to be an odd number. So this time, my sample space is what numbers? 1, 3, and 5. So now the probability that we're going to roll a 3 is going to be changed because the number of items in my sample space has changed. This conditional probability means that we've changed the total number of items in the sample space, which, yes, I heard somebody say it already, is now going to be 1 out of 3. So conditional probability means that we already know a particular event has occurred, so we have to take that into account when we deal with our sample space, which is why when you look at the formula for probability, we don't do the number of items in event E and F. We're only looking at the number of items in event E, the one that we already know has occurred. Let's see what this looks like in a larger context, because obviously that example of conditional probability was almost too easy. We had this table last class. It says the data in table 8 represent the marital status and gender of residents in the United States aged 15 years old or older in 2017. We've seen this table already. We're going to compute now some conditional probabilities. We're going to compute the probability that a randomly selected individual has never married, given that the individual is male. So we need to figure out the sample size that we're working with. We were given that the individual is male, which means we're looking at the total number of males that were surveyed in this survey. Not the total, which is what we used last time. We already know that they happen to be male. Now the probability that they've never married, given that they're male, is going to change the probability. So we're going to write down the probability that they have never married. Let me use the right colors. Given that the individual is male, will now be the number of, I really didn't leave you guys enough space, the number of male and never married over the total number of males. So I have actually highlighted for you the overlap between the never married and the males. That's the intersection point. I'm going to come down here. So sorry. I really should have left you some more room. The total number of males and not married is that one I've highlighted in pink. That's your 46.0. The total number of males, my sample size, is 126.9. So we do that math real fast. 46 over 126.9 is 0.362. So the probability that we randomly select someone from this survey and they are never married, given that we're only looking at the males, is 36%, 0.362. Part B wants us to compute the probability that a randomly selected individual is male. Oops, wrong color. Is male, given that the individual has never married. This is like the same thing, just backwards, yes?
Yep.
And I did the highlighting in a different color on purpose because we're changing our sample size, our sample space. This time when we write down our formulas, we're going to compute the probability that someone is male, given that we're only looking at the never married. We're looking for the probability that an individual is male given the individual has never married. Are you like, is it about to be the same thing?
No,
it's not.
Well, no, I'm just confused because how is it not the same as part A?
How is it? Well, okay, we're given a different set of information. The first one, we're looking at the sample space of males. That's what we were given. We know we're looking at the males. This one, we know we're looking at the never marrieds, which means we're actually looking at this total. Correct.
And then, so they're just going to switch spots?
Sort of, but our sample space also switches, not the numbers themselves switching. So again, if we follow the formula, this is the number of, this will be the green, never married and the males, given that we're looking at the number of never marrieds. And I know that it's the same words I'm writing down, but I've done a different color on purpose, because we're now looking at a different place in the graph. The number of overlap between never married and male is still the 46.0. That's still where the intersection of those two characteristics is. However, this time our total number of never marrieds is 86.1.
That's the total people who aren't married?
Correct, that's the number of people who are never married, our total never marrieds. So if we do 46 over 86.1, this is 0.534. So if we look at all of the people who have never married, 53% of them are male.
Okay.
Conditional probability is more confusing than classical because you have to pay attention to what your sample space has changed to. Okay, these double tables, that's not what they're called, two-way tables are really big places where you get conditional probability questions. And you do have a quiz next class, so be sure, you can probably be sure that there's going to be one of these things on there. Okay, let's try one more conditional probability question before we add in the general multiplication rule. Example 3 says that we are going to suppose that 12.7% of all births are preterm, meaning the gestation period of the pregnancy is less than 37 weeks. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? So what I'm asking you to find here is the probability that we are 8 pounds, 13 ounces or more, given that we are looking at the preterm babies. if we fill in our formula for conditional probability, the formula tells me that I'm going to do the probability or the number, this time we have probabilities, of 8 pounds, 13 ounces or more and preterm, all divided by the total number of, or the probability that we have a preterm baby. Yeah, that's just me trying to tell it more using less words. So 8 pounds, 13 ounces or higher. Because like preterm babies are generally small, so there's a smaller chance that you have an 8 pound, 13 ounce baby when they're preterm, right? That's just. Okay, so what were we given here? We know that 12.7% of all births are preterm. So here's the number or the probability that a birth would be preterm. We also know that 0.22% of all births resulted in a preterm baby who was also 8 pounds, 13 ounces or more. This is the intersection of these two things. This is a preterm baby who also weighed more than that weight. That's this right here. So if we're looking for this, we are going to do 0.0022 divided by 0.127. Where did I get these numbers from? Yeah, they're percentages in the problem, and when we're computing anything, we don't compute with percentages, we compute with their decimal version, so move the decimal point twice. Throw that into a calculator, which you would get 0.0173. So we have a 1.73% chance of having a preterm baby, or looking at the preterm babies and finding one that weighs more. Conditional probability is a little bit more confusing, so slow down when you see the word given, because it's going to mean that we're going to do something a little bit more complicated for probability. The general multiplication rule follows from the conditional probability rule. So what I've done here is I've retyped the conditional probability rule. And if we solve this equation for this numerator, what would we do to get this denominator to go away? We'd have to multiply it, which then gives us this general multiplication rule. That if we are trying to find P and E, the probability of E and F, we can compute that by the probability of E times the probability of F given E. Last class, we did the probability multiplication rule by P of E times P of F. We can also have this generally speaking that we know E already occurs so that F now can occur. This will help us when we have dependent events to do the multiplication rule, because last time we only had that for independent events. This is now for dependent events, but it also works for independent. Let's see what this looks like. Example 4 says probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Let's kind of flesh out what we were given here. The first sentence tells me that the probability that somebody who gets pulled over is 0.8. Are y'all cool if I just shorten that to pulled over? Okay. The second sentence tells me that the probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. You see how I wrote that down the way it was given to me? So ticket given that it was pulled over. The question we're trying to ask is, what is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Well, if we are using the general multiplication rule, that means that all we need to do to find this probability is multiply from here this formula. The probability that we are pulled over times the probability that we get a ticket and we're pulled over. Given we're pulled over.
Is Coach Mack in here?
So we're going to multiply the probability that we are pulled over multiplied by the probability that we were given a ticket given that it's pulled over. But we have those numbers. The probability that we're getting pulled over is 0.8, and the probability that we got a ticket given we were pulled over is 0.9. Multiply those guys together. 0.8 times 0.9 is 0.72. If we slow down and write down the sentences math-wise of what we were given in the problem, usually that helps us figure out what we're looking for and what pieces we already have to solve for it. So I recommend writing these sorts of things down like this so then you can see, oh, I have everything I need to solve this problem. Example 5. Suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What is the probability that the plant manager discovers at least one defective circuit and rejects the shipment? Okay, first things first, let's just figure out the probability or the number of things that are defective versus not defective in this shipment. So it says for us, how many are defective in each shipment? 5 out of 100. So using, complements, the idea of complements, how many would be not defective? 95 out of the 100. Okay. We want to find the probability that at least one is defective. Probability that at least one is defective. Last class we talked about the at least probabilities and how they're kind of difficult to do on your own. So we can use the idea of complements. So if at least one is defective, that means there could be 1, 2, 3, 4, 5, 6, all the way up to 100 being defective. How many could it not be?
95.
If it need at least one defective, 0 defective is the only other outside source, the complement here. So if we find 1 minus the probability that none are defective. Since it's at least 1, it's 1 and all the others, which means the only other option would be 0. That doesn't work. So we use the complement rule. Okay. If none are defective, that means when this, the plant manager picks up the first one, it needs to not be defective. And when she picks up the second one, it also needs to be not defective. So that probability will change to the probability that the first choice is not defective. And since we're picking a second one, we also need the second one to not be defective, given that the first one was not defective. Because we've already picked one. It's dependent. Because if the first one was defective, we would have stopped. So we're dependent on the fact that the first one was not dependent to even pick up the second one. Conditional probability. Does this make sense? This was always hardest for me to understand when I was learning probability. Like I remember being a struggle bus with this one.
This is a lot of words.
There is a lot of words, but do we understand the concept here? The first one, we pick it up, it needs to not be defective.
Okay, so because the first one's not defective.
Great, I put it back down.
Okay.
I pick up a second one.
Yeah.
The only way I would get to the point where I would pick the second one is if the first one was already not defective.
Oh,
So I'm
first
picking a
part
second
defective.
one,
Okay.
given that the first one is not defective.
Okay.
We now have conditional probability. These affect each other. Because if the first one was defective, I would have stopped. I wouldn't have even gotten to the second pull. So we're dependent on that first pull. These events are not independent, they are dependent, which means we have conditional probability. So if we go ahead and do this, okay, if we start to do this one, what is the probability that we pick one up and it is not defective? 95 over 100. So that first probability that we would pick up a non-defective one is 95 out of 100. Now we need to figure out, we put that one down. If we pick up a second one, given that the first one was not defective, these numbers will have changed. Given that it's not defective, how many items are now still in the conveyor belt?
94.
Yes. Out of how many? 99, because we've already affected one. So we're going to be looking at 1 minus 95 over 100 times 94 over 99. Because we've already picked one up, we already know about one, it's out of the list. When you calculate this, you get 1 minus 0.902, which is 0.098. So we have a 0.098 probability of at least one of these being defective when we have 100 objects on this conveyor belt in the shipment. Conditional probability is more challenging because you have to remember all of the possibilities of things that come before the action you're doing. In our last example here, we're going to kind of discuss the differences between independent and dependent events. The example is like kind of weird, but the point of the example really makes sense once we're done. It says that, by the way, whenever a small random sample is taken from a large population, it's reasonable to compute probabilities of events assuming independence. So in a study to determine whether the preferences for self are more or less prevalent than preferences for others, researchers first asked individuals to identify the person who is most valuable and likable to you or your favorite other. Of the 1,519 individuals surveyed, 42 had chosen themselves as their favorite other. So let's suppose we randomly select one of the 1,519 individuals surveyed. What is the probability that he or she chose him or herself as their favorite other? So we're looking to find the probability that the person chose self. This is just regular classic probability. Out of the information that we know, what is the number that chose themselves? 42 out of how many people surveyed? 1,519, which means we have a 0.02765 probability that we pick one and they chose themselves as their favorite other. That's classic probability, just one event occurring. If two individuals from this group are randomly selected, what is the probability that both choose themselves as their favorite other? So we're looking for the probability of, we're going to call this self number 1 and self number 2. Now this is a conditional probability problem because we have to pick two individually. We have to pick one, be like, they picked themselves, and then pick another one, assuming we've already picked one that has picked themselves. So it's dependent, and we're going to have to use conditional probability to do this multiplication rule. So we're going to find the probability that the first person picked themselves, and we're going to multiply that by the probability that the second person picked themselves given the first person picked themselves. Because we know these events are dependent. If we're going to pick two, we pick one, make sure it's self, pick two, make sure it's self. We wouldn't even pick the second one if the first one didn't pick themselves, since we're looking for both. So this kind of follows with the example we did before. What is the probability that they would pick themselves? That would be 42 over 1519. But then given that we've already picked one that picked themselves, what's the probability that's conditional of that second one? 41 over 1518, because we already picked one from both categories that got themselves. This is a very, very small number, so if you multiply 42 over 1519 times 41 over 1518, you get 0.0007468, which is 0.07% chance that two people in a row would pick themselves. Is that the wrong number? I see your face.
I got 7.4679.
79? I must have rounded up to 8. 74679, you said?
7.467, yeah.
Yeah, I've rounded up to 8. 79 would round to 8. Okay, but then this last example. We're going to compute the probability of randomly selecting 2 individuals from this group who selected themselves as their favorite other, assuming independence. So if we can assume independence, we actually go back to the old formula, which means that the probability of self number 1 and self number 2 would be found just by multiplying the probability of self 1 multiplied by the probability of the other person picking themselves. Assuming independence means that we don't have to do any of the given conditional probabilities because these 2 events are not related. In this case, both of these probabilities would be 42 over 1519 because they're not related. We're not given that the first one had already occurred when we're picking the second one.
So the number squared.
It could just be squared, yes. So 42 over 1519 squared, or you multiply it twice. We get an additionally small number, but it is a different small number. So what this means for us is, if small random samples are taken from large populations without replacement, it is reasonable to assume independence of the event. So as a rule of thumb, if the sample size is less than 5% of population size, we can treat the individual events as independent. So let's say our population, just to kind of make this make sense, if we're looking at a pond and there's 1,000 fish in this pond, and we decide to make some conclusions about the 1,000 fish that live in this pond by just picking up 50 of them, we can assume that these events are going to be independent because our sample size is so small. If we picked up 500 of them, that's a larger sample size out of the population. We can't assume independence.
Okay, so then you can, so
5%.
Small is independent.
If it's if the sample size we're getting is 5% or less than the entire population size, we can assume our events are independent. And since we can assume that independence of events, 2 events E and F are going to be independent if the probability of E given F is the same as the probability of E, or if the probability of F given E is the same as the probability of F, meaning that it doesn't matter what was happened before, what was given already, it's the same probability. So conditional probability doesn't mean anything if the events are independent. And you can prove independence by showing the opposite direction.
Just who wrote down?
Me? Okay, are there any questions about the difference between these 3 examples? We had classical probability. Well, I guess classical is wrong. Empirical probability in the classical sense. This is dependent and statements. This is independent and statements.
Okay, so this is
Bless you. Pretty much this kind of, this is why it says it's a good example to see the 3 types. I know the situation was weird. It's a good example of the 3 different types of probabilities we've seen so far. I guess not counting the 4th one of the or statements, the addition rule.